Chapter 2. So this is going to be following the CCNA cert guide books, which I just recommend if you go to Amazon and type in CCNA 200-301, there will be a cert library. It comes with 2 books, and that's what I'm going to be using to go through these chapters. So I just wanted to start off by showing you the difference in a home network and an office network. So if you check here on the left, you can see this is basically what your home network would look like. You've got your router and switch, which at your house, your router is actually a switch and a router. It does both, so it's just one condensed platform. And so is the wireless access point here on the right. So your router is a wireless router that also is a switch. So it combines basically all 3 of these, but this is just for demonstration purposes of how it would work in the real world on a production network. So let's say you've got a computer at home, you've got a laptop hooked up, both are wired, and you've got a wireless access point. Well, actually, we'll connect the laptop. No available points. I don't know how to connect the laptop in this with wireless. So we've got 2 things plugged into our router, and then you've got a tablet over here that's connected to wirelessly. So this is basically how your small home office network would be set up. Nothing too fancy. Over here on your right is how you would have routers and switches all connected. So you would have basically 3 of these. Let's say we're in an office building with 3 floors. Each floor would have their own switch so users can connect to. If you click on these and you go to config, if you scroll down, you can see that there are 24 fast Ethernet ports and then 2 gigabit ports, and we're going to go over what the difference in those 2 are in just a minute. So each of these switches has 26 ports on it, so we've got 2 connections, basically for redundancy. In case one link fails, we still have another one to use. And then we've got it all connected to a distribution switch, and this will basically manage all the VLANs and stuff like that will be hosted on here. And then finally, to get to the internet, we have our router. So all the information, if you need to talk to anything inside your own network, it won't actually have to talk to the router. Let's say you've got a file and you want to send over here to a user on switch 2. If you guys are in the same VLAN, you don't have to go to the router. It just sends the information to the distribution switch, and the distribution switch will send it to the user on switch 2. So these are the 2 different the difference in a home network and an office network. And now we're going to talk more about the things I was describing earlier, the fast Ethernet and gigabit, and exactly what all that means. So if you take a look here, on the left side I made a little chart with some different types of copper and fiber. So over here, if you see, the regular Ethernet is 10 megabits per second. The 802.3, so there's something called the IEEE, and they have these things called standards. The main Ethernet standard is 802.3, and anything that was basically a derivative of 802.3 was given its own character. So you can see here, fast Ethernet is 802.3U. Gigabit is Z. We see here we got 2 different gigabit Ethernets though, and we see Z and we see AB. Well, Z is a fiber connection. It actually doesn't use copper. So at your house, if you see your computer or PC plugged into your router, or your router connected into your wall, there's probably a little copper RJ45 jack. It looks sort of like a bigger phone jack. So if you were to cut that out, you would actually find that each little strand has these little copper pins in it, and these copper pairs of cabling that runs through it. So fiber, on the other hand, is basically glass. So what the fiber does is it sends light, and the data streams are on the light, and it bounces up and down on the glass. And we'll talk about different types of fiber later, but right now just know that fiber uses glass to transmit data and basically has it bounce around while it transfers all the way across. And if you look here, so gigabit runs at 1,000 megabits per second. Fast Ethernet's 100, and then we have 10 gig Ethernet, which runs at 10 gigabits per second, which is crazy fast. So over here on the right, these 100M, 100M, you can see fiber, the M stands for meters, and this is the distance that it can go before it starts to lose its strength. So copper can go about 100 meters before it starts losing strength, but fiber can go up to 5,000 meters. And it depends on what type of fiber you're using, and things like that will determine how far your fiber can actually go before it starts to attenuate data. So this is just a quick overview of the different types of Ethernet. Now we're going to talk about MAC addresses. So a MAC address is your computer's hardware address. This is an address. If you want to, you can actually hit Windows key and type CMD and hit enter, and it should bring up command prompt. Once you bring up command prompt, if you type ipconfig /all space /all, I have a lot of different virtualized stuff, so that's why you see tons of different ones. But we'll just come down here and look at my little Bluetooth network. So you can see it's disconnected right now, but that's not important because right now we're just looking at the physical address. So physical address, MAC address, same thing. There are a bunch of different names for MAC addresses. If you look on your phone, there could be one called a Wi-Fi address. If you look on your computer, it says physical. Some devices might just say MAC address. If you look on the back of your router, it might have it. And MAC addresses are 12 characters long. You can see each one, and they can range from the number 0 to the letter F. And it might sound weird, but these are counted in hexadecimal. So it starts at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then instead of restarting to 10, it just goes to A, B, C, D, E, and F. So if you look over here on the right side where I've got MAC addresses, so they're 48 bits, 6 bytes. Each of these characters in this MAC address is 4 bits. So that's how you get the 12. That's how you get 48, because there's 12 characters. And over here, this is actually how you look at each bit. Each bit is a 0 or a 1. So if you look here, we've got 0, 0 equals 0, 0, 1 equals 1, and basically whenever you count in binary, unlike numbers where you count to 10, we're not counting all the way up to 9 and then starting over by putting 1, 0 for 10. We're just going 0, 1 for 1, and then you start back over to the top, so you put 1, 0 equals 2. That 0 turns into a 1, so that would equal 3, and then you start over again, just like we used to do with the hundreds place and the thousands place, but instead of this time, we're only counting in binary, so there's only 2 different places you can go. So you rotate over to 100, 100, 101 would be 5, and then this has to go over here now, so 110, and so forth, all the way up to F. So that's how you count in binary and to reach different characters and how they can be represented on computers, because computers only understand bits, and these are just surges of little electricity that turns zeros and ones on and off, and that's how every single thing in a computer works. But hexadecimal is where we can represent things for ourselves, because if we just saw, let's say, if every single time we saw an F on a computer, we had to look at 111, that'd be very difficult for humans to read. So we narrow it down for us, where we just break it down to 3, 0, 2, 4, 3, 2, 6F, 4, 6, 8F. So that's just a better way for humans to understand it, but the computers, the underlying thing that they're looking at is 1111 equals F, opposed to F equals, for us, where it's just F. And that's basically the difference in how we see things compared to how computers see things. So I want to go back and actually talk a little bit more about Ethernet, and we're going to take a look at, let's see here. So if you were to walk up to your computer and pull the cable out of the back of it with the connecting to your internet and splice it and cut it open, you'd probably see one of these color codes. So these codes here are basically the standard. They've got 568A and 568B. Each of these are little copper wires running inside these little tiny strands. Each of these correlates to another strand, and that's how we get 2 different types of cabling. We've got straight through cables, where the cables match on each side. So if you look at a cable on your computer, it probably has white, orange, orange, white, green, blue, green, white, brown, brown on both sides. Whenever you actually look at the ends, they probably match to each other. But they have something called crossover cables, where they cross the pairs. So 1 and 3, and 2 and 6. So you see right here, 1 and 3, 2 and 6. So those kind of cables are used for whenever a computer or a router or something like that is connected to itself, because what it actually is doing is it's transmitting on these lines. So let's say a PC, for example. Actually, let me look and make sure before I tell you the wrong thing, because some of them transmit on pins 1 and 2, some transmit on pins 1, some transmit on pin 2. Sorry about that. Forgot I was going to go over this. Alright, so PCs, for example. PCs, routers, wireless access points. So these all transmit on pins 1 and 2. So PCs will transmit on 1 and 2. So you don't want to connect a PC to another PC, because whenever you try to transmit, the data will collide because they're both trying to transmit on the same pin. So that's when you'd want to use a crossover cable. If you're connecting to something that transmits on the same type, you need to use a crossover so it'll transmit on one and receive on the other. Switches, on the other hand, transmit on pins 3 and 6, so we want to switch those around so that way whenever, let's say you've got 2 PCs connected, if you use crossover cable, you can transmit on different pairs. Switches, they transmit on 3 and 6, so if you connect a switch to a PC, you can use a straight through cable because both the pins match on each side. If you connect to a switch in a router, you can do that as well. Hub to PC or hub to router. So hubs are an old legacy device. They aren't really used in networking anymore. And basically what they would do instead of a switch, they would transmit data out to all ports connected to it. They wouldn't select data in specific ways. So it would basically just try to send all the data out every single port, and that caused a lot of collisions in general, because if it's waiting, trying to transmit and receive, it'll actually just cause data collisions. So we don't really see hubs too much, but the CCNA covers the type of device that the type of cabling that hubs use. So they use the same pin out style as switches. So if you need a crossover cable though, so if you're connecting a switch to another switch, that would require a crossover cable. A PC to a router, or a PC to another PC, or a router to another router would require a crossover cable, and a switch to a hub would require a crossover cable. So we're going to pull back up Packet Tracer really quick. So in the modern day, you actually don't. It doesn't matter if you use straight through or crossover, because these switches are automatically able to detect it, and they'll fix it. They'll fix the problem internally, so you won't actually have to. Excuse me. You won't have to find another cable to use. But in our scenario, we're just going to take a look at how we would do it. So a switch to this router, we would use a crossover cable, or sorry, a straight through, because these are two different devices. They transmit on different things. So this crossover or straight through cable would be here. Same thing with these PCs, and basically all three of these connections would all be straight through. The wireless access point also uses the same thing as PCs and routers, so right here all of these would be straight through cables connecting to everything. And then of course the wireless tablets, wireless doesn't need a straight through or crossover cable. Over here on the other hand, you can see that these are multiple switches being connected to one switch. So we would need crossover cables connecting to everything over here. Whereas everything over here we would need straight throughs. These three over here would require crossover cables on each one of these. So 6 total crossover cables, and then 1 straight through to connect to the router. Alright, so since we've talked about straight through cables, Ethernet, we're actually going to take a look at what a frame is. So frames are basically how layer 2, or if we talked about before, layer 2 were the switches. So layer 2s use MAC addresses to communicate. So whenever a switch needs to send information, it'll actually look at the MAC address of this computer over here, and it'll send the information based on the MAC address. It'll send it down to this laptop. And if we actually click on this laptop and click on command prompt and do an IP config /all, you can see our laptop has a virtual little MAC address in here. So 00B, BE4B, 1E, 6B. So if we look at our switch, so no data has been sent on our switch here, so the laptop's not going to show up yet, but the access point has been sending data. So if we look here, this is how you actually look at the MAC address table on a switch. You just type show MAC address table, MAC-address table. So it depends on your OS of your switch. The easiest way to find it out is I would do a show MAC and then hit question mark, and it'll show you the options that are available. So it shows MAC address table is available, so we're just going to go ahead and hit that. If you hit question mark again, it shows that there's only one option now. So if there's only one option whenever you're configuring a device, if you hit tab, it'll go ahead and finish it for you. So we'll look at the MAC address table again. And we can see here that this MAC address is on port FA04. So whenever a switch needs to relay information, it'll look at the MAC address and say, oh, okay, it goes to port 4, and then it'll send the information out towards port 4. I know we didn't really look at actual configuration and stuff in the first video, and don't really worry about it in this video. I'm just showing you for an example. Later, and I think chapter 4 is when we actually get started, whenever we look into routers and switches and how to configure them and things like that. So Ethernet, like I said, uses a frame. Frames are, let's see here, where's my whiteboard? Let's see. Frames are layer 2 data that is sent. So we're not really worried about HDLC right now. This is for a different chapters. This is for chapter 3. Right now we're just focusing on an Ethernet frame. So an Ethernet frame actually looks something like this. So this is going to be a very poor drawing. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Okay, I believe that's it. 1, 2, 3, 4, 5, 6, 7, 8. Oh, there's 8. Oh no. I'm going to have to add another part. Am I right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. So each of these right here correspond to, let's say this is a frame. So this is actually the data being sent. This is just a visual representation. It's not actually sent like a cube, but it's just an easier way to take a look at it. So the first 7 bytes are called the preamble. Let's see here. And the preamble is basically used saying, hey, we're about to send some data, let's get our synchronization going. So it says, here it goes. And then we have our start of frame delimiter. A frame delimiter is basically just saying that, hey, the next address after, the next information coming after this is going to be the MAC address of where we want to go. So the MAC address is 6 bytes, just like we were talking earlier. So it sends 6 bytes of info with the destination. Then it sends another 6 bytes with the source. Says, okay, I'm going for MAC address A from MAC address B. Followed by that, let's see here. Actually, this is optional. We're not going to talk about the tag right now. This is for something later. So don't worry about the tag, so I can go ahead and erase. That's why I wanted to draw 7. We're going to worry about the type though. So whenever an IP address is sent, it's actually encapsulated into this frame. So the IP address, I don't think it's in that one. 1, 2, 3, 4. I think it's over here. Sorry about that. So whenever the IP address is put in here, they'll take 2 bytes of it and they'll insert the IP address. And this will define what type is going inside. So the type will have either IPv4 or IPv6 that's going inside of here. The next is the payload, which will actually be your data. So this data will be sent, and it can range from anywhere from 46 bytes to 1500 bytes. And then finally you have your FCS, which is used to determine if there are any transmission errors. So if there are errors, the switch doesn't really do anything about it though. It's only layer 2. So if there's an error with whenever this frame is sent, the frame is just going to get dropped. Alright. So one more thing we're going to talk about before we finish here is we're going to look at MAC addresses one more final time because there's something I forgot to talk about, and then we'll call it for this lesson. Where's my... Is it up here? Okay. So MAC address. One thing I didn't talk about is that the first 6 characters in a MAC address are called the OUI. And an OUI is basically just saying the manufacturer assigns these to a MAC address. So if we look at my Bluetooth example, whatever Bluetooth manufacturer had, all these Bluetooth devices from this manufacturer will start with this number, 302432. And you can actually look online. Let's see, Mac OUI list. And there's an OUI lookup tool. So if let's take a look, for example, 302432. 302432. So mine is saying, hey, this is Intel. So Intel is giving me this MAC address. One more thing about MAC address is that these are all universally unique. Every single device will be unique with their own MAC address, every single one of them. The only time you'll actually see that if you get some cheap knockoff from China or something like that, maybe they'll have the same MAC address. That can cause problems in your networks and things like that, so obviously you want to avoid that. But if you're interested and want to look up different OUIs, you can look up, for example, your iPhone one and pop it in here, and it'll probably say Apple Corporation or whatever Apple has on there. So know that the first six characters are the OUI, and that all MAC addresses are completely unique. Next time we're going to talk about data collisions and full duplex and half duplex. But for now, this is pretty much it for this chapter. The full duplex and half duplex is actually covered in this chapter, but I'd rather cover it in the next chapter so we can actually talk about how data is transmitted between networks. Like I said, the beginning chapters are kind of confusing because it's pretty new information, kind of top level, out of nowhere, left field kind of stuff. Nothing's really set in stone. It's just pretty confusing. But the more chapters you get into it, everything starts to make some more sense. So appreciate you watching, and hope you see the next one.